Good morning. Myself, Dr. Jagannath Samanta. I am the Associate Professor in the Department of EC. So today's lecture, I will discuss the basics of Shannon's source coding theorem. So basically, we know that the Shannon is the father of information theory. So without his dedication, we cannot progress in the digital communication system. So you know that we all are in the era of digital communication system without mobile phone or everything. So any storage system. So that is he is the main pioneer of this field. So today's lecture, basically I will discuss. These are the outlines of this lecture. So basically I will give some introduction. Then Shannon's theorem. I will discuss three Shannon theorems. I will discuss source coding theorem, channel coding theorem, and channel capacity theorem. And then I will discuss how we can measure the information. So that I will go to the details, and I also discuss some properties of information. Then we will discuss the entropy and some idea what do you mean by the information depth. So basically Claude E. Shannon, so he is basically American electrical engineer. So in the year of 1948, he he write a paper, a mathematical theory of communication that gives the idea of the information theory. So this is basically information theory. It is the hybrid field where mathematicians and the engineers, they work together. So he proposed a theory that is called the information theory. That based on that theory, the digital communication is totally developed. So what do you mean by information theory? So it is a branch of probability theory which may be applied to the study of the communication system, that with dealing with the mathematical modeling and basically the analysis of communication system. Here basically we don't consider the physical sources and the physical channel. So that don't consider. Okay, basically the mathematical modeling and their analysis part we are dealing in the information theory. So we are not consider how they are constructed. Okay, so all these things we are not. Only the mathematical modeling and the analysis part of the both mathematical as well as the communication systems. So basically, if I combine this theory, so it is basically used for the noise protection purpose as well as the efficient use of channel into a single theory. So basically noise protection, we know that when any information we are sending through the communication channel, there is a lot of noise that will disturb the information. So that information, how we can protect with the help of some coding techniques. So that noise protection is very important in a digital communication system, and efficient use because you know that whenever we are talking, so lot of information, lot of messages are generated, but all the messages are not contain the actual information. So we will use some source coding techniques so that we can effective transmission, effective codes we can use through our source coding source to the channel, actual channel. So that it combines the three basic concepts, that is the measure of source information, efficient source coding, that is the we can use the Huffman coding, Shannon coding. Then he proposed a channel coding. So the channel coding means all the information will go to the channel. So if the channel is not so much capable, we cannot send the appropriate information, so that we can. So today's you know that the video conferencing, all this type of use where the data are used, a lot of data. So if your channel is not capable, so we cannot easily send the information through the channel. So he gives a properties theorem that is used for the channel capacity. So Shannon basically he proposed the three theorem. One is the source coding theorem, channel coding theorem, and channel capacity theorem. Based on the source coding theorem, he gives that for a message, if the average code over length is L and its entropy basically we know that all the how much information per symbol, that is denoted by its entropy. So according to its source coding theorem, so L should be always greater than equal to HS. And so basically this source coding theorem, the main concept here, it is used for generally the efficient bit representation of the information source. And then the channel coding theorem, it is saying that basically if the information rate of any source, if it is less than equal to the channel capacity, C is the basically R is the rate of information and capital C, so that is basically the channel capacity. Channel capacity means per second how much data is transferred to a channel. So if R is less than equal to C, then this condition, if it is valid, then with the small error, so we can retrieve actual data from the erroneous environment. So that means we can error-free transmission is possible if R is less than equal to C. So that most important channel coding theorem is developed by Shannon also. That is a groundbreaking work of this scientist. So channel capacity theorem means whatever the channel we are using, channel basically where all the information, all the message is communicated from one point to the other point. It may be the physical channel or it may be a air or simply air, wireless channel. So he has given a capacity theorem. So the channel capacity will be equal to the bandwidth of the that particular continuous channel into log of 1 plus signal to the noise ratio. So this is C equal to B of log of 1 plus S by N, and units is bits per second. So this S is basically, it is the transmitted power and N is the noise power. So basically when we are considering here the Gaussian noise channel, that particular Gaussian noise that we are using here. So that is a very important information. So that C channel capacity, it is proportional to the bandwidth of the channel, and it is also the proportional to the signal to noise power. So higher noise, SNR means its the channel capacity should be higher. So now, before going to the details of the source coding, so what now I want to know what is the information. So information means it is directly related with the communication system. Okay, so communication means what? Communication system basically it is the transmission of information from one point to the other point with high efficiency and reliability. High efficiency means efficient uses of information. So that is very important. Otherwise, lot of bandwidth is required. So that means lot of bandwidth is required means it is a total system cost will be higher. And reliability means suppose sender is sending some data, but due to some noise, the data will be changed. So that means that is not a good communication system. So it should be reliable. Reliable means what? Sender will send, at the receiver side actual data will transmitted. Then only we can say a system is reliable. And in communication system, information is something that is transmitted from the source to the destination. That means the transmitter to the receiver section. And information signal means, so information can be simply an electrical signal, simply whenever we are typing any data in a keyboard, or picture, music, voice, all these things are that is the information. So suppose how we can give the concept of information. Suppose if I write a headlines of a newspaper, a dog bites a man. So nobody will read your article because you know that a dog bites a man, it is a natural thing. It is a frequently occurs. So here the probability is maximum. But if in a paper, if I write the title, a man bites a dog, so each reader will see that is a very informative. Okay, so that is because a man bites a dog, it is a rare incident. So that means in the second sentence we have seen that here the probability is very less, but So all the readers, they will read this article if I give these things. So we have seen that from these two sentences, we have seen that where the probability is bigger, there the chances of getting the information is very less. But where the probability is lesser, vice versa also, probability is very lesser, then the getting of information is very higher. So we can say that the information basically it is the inversely proportional to the probability of occurrence. So how we can basically the information conveyed by a message is related to the uncertainty or surprise. The greater the probability of an event of a message, lesser the information contained in it. Suppose if I say sun is rising in the east, so here the probability is maximum 1. So it is never possible to sun rise in the except east. So in that case, sun is rising in the east. So that will be here the probability information is 0 basically. So the information content is directly proportional to the uncertainty or the surprise, or inversely proportional to the probability of occurrence of the event or message. So information of an event depends only on its probability values, not depends on the content of the information. Okay, so that means whatever the message we are getting, we are giving a lot of messages, but all the messages are not giving the actual information. So information will only we will find how much probability. So based on that particular parameter we are measuring the information. So not the content, how much content it is there, that we are not considering. So how we can measure? Suppose in a discrete source means you know that it is basically it is provide a lot of information with where the discrete memoryless source basically it is a present content is only depends on the present output, not in the previous. What are the previous values that we are not considering the discrete memoryless source? So suppose m number of message or symbol if it is generating m1 m2 dot mm, and their corresponding probabilities if I take p1 p2 dot pm. So and this m1 m2 these are the statistically independent. That means what? Statistically independent means they are not related with each other. Suppose m1 and m2 they are two distinct messages, they are not depends on each other. Now the information of any kth message is mk with probability pk. So ik self information, this ik will be log of 1 by pk. So I can say self information or the information of any message of kth any message, it will be always equal to a log of 1 by pk. So we can also write this expression is equal to minus of log of pk base b. This base b is a very important. So based on this b we will find the unit of the self information. So based on the base, if base is 2, so the unit of information will be bit, and if base is natural e, so it will be the nat, unit of the information will be nat. If the base is 10, so the unit of information will be decit or Hartley. Now what are the properties of information? So if any message whose probability is maximum, say it is 1, then we can claim that here no information. So ik will be 0 if pk is equal to 1. So how we can comment that? If we are absolutely sure about an event, then it convey no information. Suppose if I say sun is rising in the east, so in that particular sentence there is no information, because here the probability is 1. And probability values, we know that it is the belongs to less than equal to 1 and greater than equal to 0. So so that's why the ik, that is the self information, is always greater than equal to 0 value. Self information cannot be a negative quantity. So its value, minimum value is always 0 and the maximum value should be infinite. So it should be ik should be greater than equal to 0. And ik for a two message, so k where whose probability pk is less than equal to pl, so ik greater than equal to il will be there. So more the less probable event will give the higher information. So if two messages, kth message and the lth message, if they are statistically independent, their information will be the summation. So ik comma l equal to ik plus il, where ik and lth are the statistically independent, they are not depends on. If there are two or more independent messages, then the total information conveyed is sum of the information associated with each of the message individually. So if the m number of messages we have, if they are statistically independent, their total information will be summation of that I1, I2 like that plus In. So we know that for a mth, suppose any discrete memory resource, if it emits m number of different messages, independent different messages, so m1, m2 dot mm with probabilities p1, p2 dot pm. So, and we know that the summation of all the messages will be always equal to their probabilities. Probabilities of their all the messages equal to 1. So, and we are taking a very large sequence L. So, for M1, so P1L, P2L. So these are the numbers will be there. And if I take the whole mth symbol, so their self information will be I1 equal to, so P1 log L log of 1 by P1. So in the same way, mth symbol we are taking, so the total number of information will be I total equal to I1 plus I2 plus dot Im. So then my entropy value H entropy, we know that it is the average information per symbol. So that value will be equal to I total by L. So that can be denoted by P1 log. So if I write in a single, so it will be minus of summation I equal to 1 to m P1 Pi log of Pi to the base B. So these are the entropy value for a particular source. So that is very important. Now what will be the entropy, unit of entropy? Entropy is so based on the base of the logarithm. If base is 2, so the entropy unit will be bits per symbol or bits per message. If the logarithm base is E, then it will be nats per symbol or nats per message. If the logarithm base is 10, so we can see that the entropy unit will be digit per symbol or bits digit per message. So for a source with 2 messages with their maximum entropy value H max equal to 1 bit per message when they are equal probable. Suppose 2 event M1 and M2, if they are equal probable means P1 and P2 value if it is then same, then the H max entropy maximum it should be value will be 1 bit per message. Similarly, for m number of equal probable event, so the maximum entropy value will be log m to the base 2 bits per symbol when all the messages are equal probable. So that will be the maximum of entropy value. And if I plot the probability versus entropy maximum, so you will see that when the probability value is 0, so the entropy it is getting 0. And if probability value, we have already proved that probability value if it is 1, then the entropy value it will be 0. And if any event probability value is 0.5, we have seen that the entropy we are getting the maximum value and its value will be 1 maximum value for a 2 event. Now what are the properties of H? H will be equal to 0 when the probability of all messages except one of the source is 0. The source emit one and only one. Suppose any source which is emitting only one message, that means the probability will be 1. So in that case the entropy value will be 0. So for a single message from for a particular source, if it is emit only one, then its entropy value will be 0. That will be its lower bound. And if m equal probable event, if it is generated from a source, and that maximum value entropy we are getting, that is equal to log m to the base 2. So we can say that entropy value is bounded should be less than equal to log m to the base 2 and greater than equal to 0. So that is the bound, we can say upper bound. This value is upper bound log m to the base 2 and 0 is the lower bound. Within that range we are getting the entropy of a particular source. Now the information rate basically capital R, it is the average number of bits per second that is passing through a channel, and it will be equal to messages per second into bits per message. So we can R equal to R small r into H, that is the bit per second. So R is the number of messages generated from a source per second. So R capital R, that is the information rate, that will be equal to small r into H. Small r, that is the rate of message generation from a particular source, and H is the entropy. They are related. So information rate and entropy value, they are directly proportional to each other. So thank you. This one.